changing between
This
the
meeting
screens.
is being recorded.
Okay, so we are going to look at conditions under which such models admit trajectories which satisfy the so-called SRRT conditions. SRRT stands for slow roll with rapid turn, in a certain sense. I will explain. It is in fact rather non-trivial to find such trajectories, and these consistency conditions impose some approximate constraints between the potential of such models and the metric on the target space, under which you have a chance of finding such trajectories. And we are going to impose these conditions strictly. This is going to lead to the so-called SRRT equation, which turns out to be a geometric PDE, which relates the metric and the scalar field metric and potential of such models. And then we are going to analyze this equation and show that if we fix the conformal class of the scalar field metric, it reduces to a first order contact Hamilton-Jacobi equation. So that's a very brief review of what I'm going to explain. Now, why is this important in cosmology? Because it's in fact rather non-trivial to find models which admit SRT inflation, and this consistency conditions gives you an a priori way to identify such models, so to rule out most models that you can write down without trying to actually compute trajectories by hand, because there's a continuous infinity of trajectories since they depend on the initial conditions. Okay? And so it provides a selection criterion, but we also have a constructive way to build such models by attempting to solve this contact Hamilton-Jacobi PDE, which turns out to be regular in the sense of Crandall and Lyons. Not now, please. And therefore can be approached through the method of viscosity solutions. Okay, good. So this is a scheme of my talk, the outline. I will start with a brief introduction to two-field cosmological models. It's mostly for the benefit of people who are not familiar with this, for example, students. And then I will recall the definition of reduced observables, and I will give a very brief description of the point of the origin of these consistency constraints, which exist much more generally, not just for SRRT inflation, but that's another discussion. Then I will recall what are called the adiabatic and entropic equations, which are well known in the subject of multi-field cosmological models, the definition of various kinematic parameters. I will describe the slow roll and rapid turn regimes. I will define something called the adapted frame, discuss natural coordinates on the phase space. Then I will finally discuss consistency conditions, and then I will go into the discussion of the SRRT equation and its the fixing of its conformal structure. Now, most of these are quite simple. The discussion of the SRRT equation will occupy most of the second part of the talk. Good. So what are these two-field cosmological models with oriented target space? So we impose orientability. It can be easily relaxed, but it just makes things a bit more complicated, and I don't want to do this here. So by definition, a two-field such models are parameterized by something called an oriented scalar triple. So by definition, a two-dimensional oriented scalar triple is an ordered system, MGV, where M together with G form a connected, oriented, and borderless Riemann surface, which is called the scalar manifold, and V is a smooth real-valued function called the scalar potential defined on the manifold M. Okay, so M is simply a surface which I assume to be oriented, smooth, of course, but I do not assume compactness. I assume only that.
When you say surface, you mean dimension 2?
Yes, surface means a manifold of dimension 2, a smooth manifold of dimension 2, which I assume to be connected and borderless, so it has no boundary, and I also assume to be oriented. Okay, I endow it with a Riemannian metric G, okay, and M together with G is now a Riemannian 2 manifold, which is oriented, which is called the scalar manifold. And V is a function defined from M with values in R, which I assume to be smooth. V is called the scalar potential. So together, this data, M, G, and V, form something that I call an oriented scalar triple. It's just a definition. Now, the assumptions that are typically made in order to build a physically good two-field cosmological model from a scalar triple are the following. First of all, this Riemannian two-manifold MG is required to complete. This comes from the need to ensure conservation of energy. Of course, formally you can relax this mathematically, but then you may violate conservation of energy, which is unphysical. And the second assumption, that's technical, it's mostly to avoid technical problems and problems with the physical interpretation, but those are secondary. The second assumption is that V is strictly positive everywhere on M. So it's really a function from M with values into the positive half axis, which is smooth. Okay? Now I will use assumption 2. For some of the discussion, I won't worry about completeness. For some of the mathematical discussion later. But of course, for physics application, you will also have to impose completeness, and I will comment a little bit about that. Okay? Good. Now, if I give you a scalar triple, then you can associate to it a model of gravity coupled to scalar fields defined on R4. So R4 will be my space-time. Of course, R4 with a standard differentiable structure. Okay, so it's given by a functional of little g and little phi, where little g is a Lorentzian metric on R4, which I take to be a mostly plus signature. So at every point, little g is diagonalizable, and on the diagonal I have I can bring it to the form in which it has eigenvalues -1, +1, +1, and +1. So that's called the so-called mostly plus convention. Okay, and little phi is a smooth, it's a map, okay, from R4, valued in this surface M, which I will take to be smooth. Okay. So the functional, the action functional which defines my model is a functional of little g and little phi, which is written here. Okay, it's formally an integral over R4 against the volume form of R4 together with G, the volume form of this pseudo-Riemannian metric little g, Lorentzian metric, and the Lagrangian that's written in within the square brackets, where big M is something called the reduced Planck mass. It's the Planck mass measured in certain units. Little phi pullback of G is the pullback of this metric, Riemannian metric G that I considered on M through the map little phi. Okay, that gives me a symmetric two-tensor defined on R4, and I take the trace of the endomorphism of the tangent model of R4, which is obtained by raising any of the two indices of this symmetric tensor. That's an operation that's well known in Riemannian geometry. It's usually denoted by trace little g. So this is what I have here. Of course, everybody will recognize that this is just the Lagrangian of the nonlinear scalar model for maps from R4 into this Riemannian manifold and little g, into the scalar manifold. But to this nonlinear sigma model, I also add a potential term, which is simply given by the integral against the volume form of little g of V compose phi. So V compose phi is now a smooth map from R4 into the positive half axis. Okay, and here I have the standard Einstein-Hilbert term, is the first term in the square brackets, where R of little g is just the scalar curvature of this Lorentzian metric G. That's just a standard Einstein-Hilbert action. So you have standard coupling of the Einstein-Hilbert gravity to this nonlinear sigma model modified by this scalar potential term. Okay. Now it will be convenient.
May I ask the question? So phi has values in some two-dimensional Riemann surface, yes?
Yes.
For instance, phi might be a complex function on a Riemann sphere.
Yes.
Or with values on a Riemann sphere.
Absolutely.
Suppose phi is constant. What is the second term?
0.
Phi is a constant function. What is
Zero.
the second term? What is phi star of G?
It's 0. If phi is constant, then the pullback of G by a constant function is 0.
0. Okay. Thanks.
Yeah. Yeah, of course. So this is, of course, this is if you didn't have the coupling to Einstein gravity and to the scalar potential, and then the equations of motion that you would get from this action would just be the equations for pseudo-harmonic functions. So of course, constant function is pseudo-harmonic, and the corresponding pseudo-harmonic energy, which is this trace G phi, is 0. Okay. Good. Now, it will be convenient for later to define the rescaled Planck mass m0, which is just square root of 2 over 3 times m. This is just to remove some factors, some uninteresting factors from some formulas, to make some formulas a bit nicer looking. Okay. Now, how do you get from here to a classical cosmological model, by which I mean a model which where I don't try to consider even the classical fluctuations around the classical solutions, let alone to try to quantize it, let's say, in first order canonical quantization. So in order to get this classical cosmological model, you take little g to describe a spatially flat Friedmann-Lemaitre-Robinson-Walker universe. So this means that the corresponding squared line element of little g is given by this formula. So it's minus dt square plus aft square dx vector square. So dx vector square means dx1 square plus dx2 square plus dx3 square, where I considered Cartesian coordinates on R4, where the first coordinate is denoted by t, the coordinate x0, and the other 3 coordinates, x1, x2, and x3, are grouped into this vector, x vector. Here, a of t is strictly positives, and a will be, in fact, a smooth function. In general, you can take this smooth function to be defined on an open interval with values in R, but I will not go into those details. Are not very important here. And besides taking this ansatz, the FLRW ansatz for the metric, which is of course well known, you also take phi to depend only on this variable little t. The variable little t is generally denoted, is generally called the cosmological time in cosmology. Okay. Good. So if you make this ansatz and plug into this section and consider a variation problem, you get certain equations which describe the solutions of the variation problem. So to formulate these equations, it's convenient to define 2 objects. First of all, the Hubble parameter, which is just a function of t, which is defined as a logarithmic derivative with respect to t of a. So the notation dot stands for the derivative with respect to t of any function which depends on t. And it is also convenient to define the so-called rescaled Hubble function. This is a function defined on the total space of the tangent bundle to the surface M. Okay, so this Tm is a 4 manifold, okay, with values in the positive half axis. And it's defined by this formula. So for every u, which is an element of Tm, you consider the norm of u with respect to this Riemannian metric G that you had on M. You square that, and you add to it twice the value of the potential evaluated at pi of u, where pi is the projection, the bundle projection of the tangent bundle to M. So pi goes from Tm into M. Pi of u is a point in M, so you can evaluate V at the point pi of u. You get a real positive number, to which you add another real non-negative number, namely the norm of u with respect to the Riemannian metric G squared. And then you take the square root. So clearly you get a smooth function, because it is smooth because we assume that V is strictly positive. So you never hit the value 0 where the square root might fail to be smooth. So it is a smooth function from Tm into the positive half axis. Okay, so that's a rescaled Hubble function. So now the proposition is, which is follows from a simple variational computation, is that when h of t happens to be strictly bigger than 0, which is what we assume throughout, which is standard in cosmology, the equations of motion that follow from this section that I had before are equivalent with two conditions, namely with the so-called cosmological equation, which is written here, together with the so-called Hubble condition. Now, the cosmological equation is a nonlinear geometric ODE of second order. So here, nabla t means the covariant derivative with respect to the Riemannian metric G on my surface, okay, a phi dot of t with respect to phi dot of t. So nabla t is a shortcut for nabla phi dot of t of phi dot of t, okay? Then the second term, so we have this nabla t of phi dot of t. The second term is 1 over m naught. So you can see now why I introduced the rescaled Hubble constant to simplify this prefactor so that I don't care factor the square root of 3 over 2 or 1 naught. Multiplied by h evaluated at phi dot of t. Here calligraphic h is the Hubble function. So you view phi dot of t as an element of the tangent bundle. So you can evaluate the rescaled Hubble function on phi dot of t, and that gives you a positive real number, and you multiply that with the vector phi dot of t, okay? And then the last term is the so-called gradient term. So here I have the gradient vector field of v with respect to the Riemannian metric G, which is a tangent vector field to my surface M, and I evaluate that vector field at the point phi of t, which is a point in M. So you do this for t belonging to the interval of definition of this function a of t, which you can take, for example, to be just a whole real axis r when you have
excuse me, phi dot is a tangent vector to M, yes?
Yes, yes.
So this nabla is also with respect to phi dot?
Yes, nabla t of phi dot of t is a shorthand for nabla with respect to phi dot of t, phi dot of t.
You should write nabla phi dot, no? Which is
yes,
normal for geodesic equation.
Yes, of course, of course.
So
this
the
is
first part is a geodesic equation.
Yes.
The first term.
Exactly. If you neglect the second and third term, that's a geodesic equation for phi. Okay, but I write it like that because it's very customary in cosmology to write it like that. So as I said, this is just a shorthand. Nabla t of phi dot of t just means nabla phi dot of t of phi dot of t. So indeed, if you neglect the second and third terms, this is just a geodesic equation. And that's a very important observation. So if you neglect the first and second term, this is just a gradient flow equation. If you neglect the first term, this can be written as by some reparametrization as a gradient flow equation. So the equation becomes a reparametrized gradient flow equation if you neglect the first term. And if you neglect the second and third term, you have the gradient flow equation. So if you vary the parameter m naught, you in a certain sense interpolate between gradient flow, reparametrization of the gradient flow and the geodesic flow. And that's a very important thing, and I have a paper a few years ago which discusses the implications of this and the various dynamical regimes and the notion of dynamical RG flow, which relates them and a whole long story, but I don't want to go into that. So this equation is in fact very interesting because it somehow interpolates between two classical flows in a theory of dynamical systems, namely the geodesic flow and the gradient flow. But the gradient flow limit is singular in the sense of Poincaré, so you can do a form of singular perturbation theory around the gradient flow limit and the form of non-singular perturbation theory around the geodesic flow. So there's a long story and very interesting one, but I don't want to enter into that. Okay? So the equations of motion are, as I said, are equivalent to this equation, the cosmological equation, which is a geometrical ODE of second order, together with a Hubble condition. The Hubble condition tells you that this Hubble parameter, which was a logarithmic derivative of the scale factor, A is called the scale factor, A with respect to cosmological time, must be equal at any value of the cosmological time to the quantity in the right-hand side, which is 1 over 3 m naught times this Hubble function evaluated on the vector phi dot of t. Okay, so a Hubble condition determines the Hubble parameter in terms of a solution of the cosmological equation. Yes?
What happens if H is strictly negative? Are there no solutions, or?
There are solutions. So if H is strictly negative, you have a solution with the opposite sign, but that corresponds to there's some kind of symmetry which relates solutions with positive and negative H. So you actually don't gain anything by
thank you.
By taking negative H. Yes. What is more interesting is that.
Sorry, I also wanted to ask a question, a very general one. Since we are trying to keep with physics, so what's the interpretation of this M, of this surface? Because the equation of motions are for two things. First is this function A.
You mean the
second is the function I, yeah?
You mean the
Hubble condition.
The Planck mass? So M naught is just the rescaling of the Planck mass, and the Planck mass is just a Planck.
No. But there is the proposition, yes?
Yes.
There are equations for two things. First is this curve phi, and the second is encoded somehow in the Hubble condition, and this is probably the equation for the function A, which is part of the metric on R4.
Yes, so the Hubble condition determines the scalar factor, this A of t, up to, of course, a multiplicative.
And my question is, what is the physical interpretation of the surface M?
Of the surface M.
The surface, this two-dimensional manifold.
Yes, it's a way to parameterize two scalar fields. So if you choose local coordinates on this surface calligraphic M, then you can write phi of t in those local coordinates as phi1 of t, phi2 of t. So you can view phi of t as a pair of two real valued functions. So this means that locally phi of t is just a pair of two real scalar fields. So that's why this is called the two-field model. It's a model for with two real scalar fields. However, this decomposition of phi into two real scalar fields depends, it's only locally valid and it depends on the choice of local coordinates. So the whole point here is that I want to have a fully geometric description of everything, which is independent of choices of coordinates. It will be important for me later, which is, of course, very standard in the theory of nonlinear sigma models. So this is somehow a reduction, a time-like reduction of a nonlinear sigma model. So you could, if you looked at this full action and you looked at full solution of the variational equations for this action, you would get the Einstein equations, and then you would get as equation of motion for phi, you would get some kind of nonlinear sigma model deformed by a gradient term which comes from the potential. So this fits very well into the theory of reductions of nonlinear sigma model. So that's another long story that I could go through. But yes, it's a theory with two real scalar fields, morally speaking, locally on M. But that decomposition depends on the choice of coordinates on M. Choice of local coordinates on calligraphic M. Does this answer your question?
Yeah, thank you.
Okay, good. So now the solutions of the cosmological equation. So I consider solutions valued in M. There are functions from I into M, so curves, where I is a non-degenerate interval. Non-degenerate means that the interval is not reduced to a point. So I can be an interval which is open, closed, or semi-closed. A closed interval could be of the type, let's say, alpha, comma, alpha, so it could be reduced to a point, and I rule out that case because I'm not interested in that kind of curve. So I take I to be a non-degenerate interval in the sense it is not reduced to a point. But it can be any kind of interval, right? Again, open, closed, or semi-closed, okay? So phi is just a curve in M, okay? And I'm interested in smooth solutions, okay? Which, of course, because I took everything to be smooth, can be easily arranged by using regularity theorems. So smooth solutions of the cosmological equations are called cosmological curves. This is just terminology. Now, It is a standard technology by coming from a theory of double tangent bundles and semi-sprays and so on, which tells you, so that standard theory tells you that a geometric second order ODE, and this is manifestly geometric because all operations used there are geometric, can be written in terms of a semi-spray or a second order vector field defined on the tangent bundle of M. So it defines a geometric dynamical system on Tm. So this comes from the fact that this is a geometric expression of the fact that locally, if you choose local coordinates, this can be written as a system of second order ODEs, and any such system can be rewritten by introducing auxiliary variables, so denoting the first order derivatives by something, as a system of 4 first order ODEs. If you want to do this geometrically, you have to do it using the theory of double tangent bundles and the second order vector fields, also called semi-sprays, and you can do that. So what this tells you is that there exists a so-called cosmological semi-spray, which encodes this equation. And that cosmological semi-spray is a vector field defined on Tm, which obeys second order vector field conditions. So Tm together with that cosmological semi-spray defines a dynamical system whose phase space is Tm, and that dynamical system is called the cosmological geometric dynamical system of your scalar triple. So again, I have a paper which you can find on the archive where I discuss this in detail and I give you the expression of this cosmological semi-spray and whatnot. And now, of course, any cosmological curve defines a cosmological orbit, which is a curve in the tangent bundle to M, which is given simply by taking the value of phi at a point and the value of phi dot at a point. Of course, implicitly phi dot is just a vector in Tm, so it includes its base point. So this notation is a bit redundant. So you could also say that O phi of t is just phi dot of t as a vector in Tm. So this means that if I give you a solution of this cosmological equation, it is in fact a projection through the natural projection of the tangent bundle to M of a more important curve, the cosmological orbit, which is a solution, which is an integral curve of this cosmological dynamical system. And of course, there are some general properties of this cosmological dynamical system. Some of them I discussed in one of my papers. I also have a never-ending preprint in which I discussed much more sophisticated things. The problem here is that, of course, Tm is a non-compact phase space, and you have to control the behavior of curves at infinity and so on, and I have some results in that direction, but I'm not yet satisfied with, I think some of them can be improved, and I've been postponing that one. So, of course, there's a lot that you can say about this kind of dynamical system using standard theory of geometric theory of dynamical systems, and also things that you cannot say just from generalities, but you can say by exploiting the structure of this cosmological semi-spray, which comes from the structure of this cosmological equation. The most interesting things, in my opinion, that can be said are those which relate to this dynamical RG flow that I mentioned before, which admits a formulation in the sense of dynamical systems. And there's another long story that I don't want to go into during this talk, because it's not the focus of this talk. Okay. Any questions, further questions about this part? Okay. If there are no further questions, then let me mention one more thing, namely the notion of observables and their reduction, and give a very briefly the idea of functional conditions. So to define observable, of course, an observable will be, morally speaking, some kind of function of phi of t, a classical observable. I'm talking about classical observables here. Phi of t and its higher derivatives with respect to time. So to describe this geometrically, of course, I will consider the case jet bundle of curves in M. Okay? So of course, J1 of M is just a tangent bundle to M, it's Tm. And I say by definition that a classical cosmological observable of order K is a function defined on some open subset of Jk of M, of the case jet bundle of curves in M, with values in R. So I consider scalar classical cosmological observables. Of course, you can consider tensor-valued cosmological observables, which are sections of some pullback of sections of some bundle of local sections of some bundle of tensors defined on this surface M. But here I consider just scalar classical cosmological observables and real scalar cosmological observables. So they are functions defined on some open, non-empty open subset of JK of M with values in the real numbers. You can take them to be even discontinuous, but of course the most immediately interesting for us are those that are at least continuous. The nicest ones are those which are smooth. Okay. Now observables of order 1, so which are defined on some open subset of J1 of M, which is just Tm, okay, are called basic observables. Now, any observable of order K can, of course, be reduced to a basic observable using the cosmological equation. So this process is called on-shell reduction of observables. This comes from the fact that, of course, cosmological equation can be formulated. It's a geometric ODE. So one way to formulate it geometrically is to use this, to lift it to a dynamical system on Tm. But another way, which is, of course, much more general, is to formulate it using a constrained surface inside the second order jet bundle. And because this is autonomous in the sense that you can separate the second time derivative from this equation, you can use that to reduce higher order observables to first order observables. So that process is physically called the on-shell reduction of observables. On-shell refers to the fact that you are using the equation of motion. So you view the cosmological equation as the equation of motion of your system. Okay? So if you follow this on-shell reduction of observables, you can reduce modulo the equation of motion, modulo the cosmological equation, any case order observable with k bigger or equal than 2 to an observable with k equal 1. So an observable which is defined on an open subset of Tm, which, as I defined before, is called a basic observable. All observables can be reduced to basic observables, modulo the equation of motion. So there's a notion of slow roll and slow turn parameters, which you will see in a moment. So these kind of parameters, they are in fact real valued observables, and they can be defined for various orders. So using this process of on-shell reduction, they can be reduced on-shell to produce basic observables, and that's a very important observation, conceptual. Thus, local conditions on a cosmological curve which constrain such parameters, and these conditions are very common in cosmology, can be formulated in conditions as conditions on points of the tangent bundle of them. In other words, they become modulo the equation of motion conditions, they become conditions on the state of this cosmological dynamical system that I mentioned before. And as an application of this, I want to just give you the basic idea of how you end up being able to derive consistency conditions, which will appear in a moment, for various types of processes that cosmologists are interested in. So let us consider 4 smooth basic observables defined on the same, on some common open subset of Tm, non-empty open subset of Tm, real valued smooth basic observables, which are functionally independent for generic model parameters G and V. So these observables, of course, they can depend on the parameters of the model, and the parameters of the model are this Riemannian metric on my surface and this scalar potential, G and V. Because the dimension of the total space of the tangent bundle to M is 4, M is a surface, recall that M is a surface, it follows that if I take a point U in this open set calligraphic Q subset of Tm, and I impose the 4 simultaneous conditions that F1 of U vanishes, F2 of U vanishes, up to F4 of U vanishes, I have 4 conditions which are functionally independent, right? And therefore, these conditions select a discrete set of points in the tangent bundle of them for generic values of parameters, right? So I assumed that the observables are function independent for generic model parameters G and V. It follows that there cannot exist any cosmological orbit which satisfies these conditions, because the image of a cosmological orbit is a curve in M, and that has a continuous infinity of points, right? Because I assumed the defining interval of a cosmological orbit to be non-degenerate. And you cannot fit a continuous infinity of points into a discrete subset of Tm. So it follows that no cosmological orbit can satisfy these conditions unless G and V satisfy some kind of constraint, right? If for generic model parameters G and V, these functions are functionally dependent, right? And if that implies that you cannot find a cosmological curve which satisfies these conditions at every point on the curve, or a cosmological orbit which satisfies these conditions at every point of the orbit, then it must be that the model is non-generic, that some conditions have to be satisfied between G and V, in general some differential conditions, in order for this system, for these functions to become functionally dependent. Okay?
But why do you want this type of orbits? You mean a non-discrete when you say cosmological orbit, yeah?
Yeah, so you will see in a moment that for certain kind of processes that are important for inflation, for example, for SRRT inflation, you end up having this kind of conditions imposed simultaneously. And the point of my argument will be, well, I made this argument in a published paper with Lilia Angelova, that exactly this. You have too many conditions and they cannot be functionally independent. Therefore, there will have to be an equation satisfied by the model parameters in order to satisfy all those conditions simultaneously. So in other words, certain types of curves which are relevant to certain types of inflation can only be found for non-generic choices of model parameters. This is what we call consistency
somehow
condition.
say that physics requires to restrict the metric G and the potential V.
Yes, exactly. In order to realize certain kind of inflations, you will have to impose this kind of conditions. You will see exactly what the functions will be simultaneously, and you will never find a cosmological curve whose cosmological orbit satisfies these conditions unless there is a constraint between G and V. That's called the dynamical consistency constraint. That's what we call it.
Okay.
So here I give you a very abstract version of this argument, just to tell you that it's very generic. It's a very elementary thing. It's an application of the implicit functions theorem. So there's no conceptual mystery where this comes from. Okay. Of course, the application will be to some very specific choices of these functions. And the key to this argument is that those functions which come from certain cosmological parameters, they are actually on-shell reductions of certain cosmological observables. So you first on-shell reduce, and then you apply this kind of very general argument. Okay. Now, if instead of requiring that these equations are satisfied with equality to zero, strict equality to zero, if you require that the absolute value of these functions is much smaller than 1, the same kind of argument shows that G and V must approximately satisfy the differential equation. So that's
what do you mean by smaller, much smaller than 1? Because F multiplied by 100 is also a basic observable. So
I mean,
one has no meaning in this setup.
Well, I mean, but then 95% of mathematics papers are meaningless when they write much smaller than 1. So much smaller than 1, of course, means just much smaller than 1. What, of course, is intended is that there will be ideally some kind of asymptotic expansion in 1 over absolute value of in this parameter's absolute value of fj. But of course, to prove that you have an asymptotic expansion, you have to prove asymptotic bounds. But I think that it's absolutely common in pure mathematics to talk about something being much smaller than 1. Okay. Even when you cannot, or you haven't yet proven that there is an underlying asymptotic expansion. But yes, the intention is that if you want a theorem, there will be some kind of asymptotic expansion in the absolute values of fj's. That's what I mean. Okay? So the same argument shows that in this case, G and V will approximately satisfy differential equation. And you will see in a moment how we will apply it concretely. Here, I just wanted to give you a very general formulation of this, so you can see this is basically an argument that comes from the implicit function theory. Good. Now, now I'm going to go into the definition of the observables that will appear in my argument, the cosmological observables. So for this, I start with this is very well known in cosmology, but I will recall it for those who have never seen. This is multi-field cosmology, okay? So I will start by recalling the adiabatic and entropic equations. So for this, you just consider the Frenet moving frame of a cosmological curve. So you take a cosmological curve from I to M, it's smooth, so it has a moving frame. Because M is oriented, I can consider the positive Frenet frame. T is the tangent vector to phi at some t, which is an element of I, some cosmological time t, which is an element of I. And N is the normal vector to t, chosen such that t and N form a positively oriented basis of the tangent space to my surface M at the point phi of t, right? That's what I mean by a positive Frenet frame. Okay. Now, of course, one way to formulate the relation between N and J is to say that N of t is equal to J times T of t, where J is the value at the point phi of t, which is a point in M, of the complex structure defined by the conformal class of the metric, Riemannian metric G, relative to the given orientation of M, right? So I remind you that if I give you a Riemannian two-manifold, which is oriented, so which is exactly what I have, this Calin manifold is a Riemannian two-manifold, which is oriented, then there is a one-to-one correspondence between conformal classes. If I give you a two-manifold which is oriented, which is this M, my target manifold in my application, then there is a one-to-one correspondence between conformal classes of Riemannian metrics on M and positive complex structures defined on M, where a complex structure is called positive if the orientation induced by that complex structure on M agrees with the initially given orientation of M. Right? So if I give you an oriented two-manifold, of course, you can have two types of complex structures, those which induce the orientation of M and those which induce the opposite orientation. Those which induce the orientation of M are called positive complex structures. And the positive complex structures, and that's a very classical result, are in one-to-one correspondence with conformal equivalence classes of Riemannian metrics defined on M. Right? So since I have a Riemannian metric on M, I can consider the corresponding positive complex structure, which I call J, and then J corresponds to a rotation by angle plus pi over 2, where plus refers to the fact that the orientation is in the counterclockwise direction with respect to the orientation of M. And therefore, that's exactly what you need to, the kind of rotation that you need to apply on T of t in order to obtain N of t. Right? So N of t is just equal to J times, J, this J is an endomorphism of Tm applied on T of t. So that's an elegant way to express the relation between N and J for this positive Frenet frame. So T of t is just a normalized tangent vector to phi at the point T. Okay. So now, one way to explicitate the relation between the complex structure determined, positive complex structure determined on M by the conformal class of G and the metric G itself is written here. So you consider the volume form of this Riemannian metric G relative to the given orientation of M. And then you can recover the complex structure, the positive complex structure J determined by the conformal class of the Riemannian metric G from this formula. So omega of uv is equal to G of Ju, G applied to Juv. So omega again is the volume form of G, and G is just the metric itself. Here U and V are arbitrary tangent vectors to M at the same point of M, of course. So U and V are U, comma V is an element of Tm cross Tm over G, the relative Whitney product. Okay. So that's the explicit formula, which of course you can prove in various ways, and I discuss this in my preprint. You can see from this formula that the relation is purely algebraic. So it tells you that J is determined by some algebraic function, which of course you can write down, but is not interesting for the purpose of this talk. It's a nonlinear algebraic function of the metric G, right? Because locally in some system of coordinates, for example, the volume form is given by the square root of the gram determinant of G, which is a algebraic function of coefficients of G at that point. And here you have the coefficients of G themselves, which appear. So J is an algebraic function of the coefficients of G. Okay? It doesn't depend on the partial derivatives of G or 1. No. And you can write it explicitly in local coordinates, for example. Okay, that's an important observation. So, with all these preparations, let me consider sigma to be let sigma be an increasing proper length parameter for phi. Therefore, this sigma is a norm of phi dot of t times dt. Okay. Then, if you look at the cosmological equations I wrote before, you can project it, of course, along the directions determined by the tangent vector and this positive normal vector, t and n. And you get two equations. These two equations are called the adiabatic in the cosmology literature, the adiabatic and entropic equations, and I wrote them here. Okay. Where I introduce some notations which are, again, classical in cosmology. So, h of sigma sigma dot is square root of sigma dot square plus 2 v of sigma. So that's an incarnation of this Hubble function. Vt of sigma is by definition the tangential derivative of v. Tangential means in the direction determined by the normalized tangent vector t to phi. So it's the differential of v at the point phi of sigma applied to this normalized tangent vector t of sigma. And Vn is a normal derivative, where normal refers to this positive normal vector n of the Frenet frame. So it's by definition the differential of v at the point phi of sigma applied to this normal vector, a unit normal vector n of sigma. So, of course, J is a rotation operator. So, since T was a normalized vector, normalized with respect to the Riemannian metric G that I have on my surface, it follows that n of T is also a normalized vector. It's a unit norm vector with respect to the same Riemannian metric, right? J is just a rotation by angle plus pi over 2. That's, of course, at each point of M, so in the corresponding, the tangent space to M at a point of this surface M carries a metric, right? An Euclidean metric. It's a Euclidean vector space, which is oriented because M is oriented, and you can consider rotations of angle plus pi over 2. It's an oriented plane, every such oriented Euclidean plane, every such tangent space. You can consider rotation of angle plus pi over 2 in that oriented Euclidean plane. And finally, this big omega is just this quantity. It's minus the Riemannian metric G applied to n and to the covariant derivative of t in the direction phi dot of t. So again, as Janusz pointed out, nabla t, of course, mathematically is just nabla phi dot of t, but this is the standard of use of notation in cosmology. So nabla t means nabla phi dot of t with respect to the vector phi dot of t of this normalized tangent vector t. So this is just a notation. So again, going back, these are the so-called adiabatic and entropic equations. They are simply the projections of this cosmological equation along the two directions of this positive Frenet frame, the positive moving frame of a given cosmological curve. Okay. So now, using these two projected equations, you see that it's natural to define certain parameters, which are very standard in multi-field cosmology. So here you have two-field cosmology because you have only two real scalar fields locally.
Can we have a break, maybe?
Sorry? A break already, okay.
Yeah, this is what I wanted to say. We should plan a break soon.
Okay, so let me go through two more slides because this is very easy. This is just our definitions. And then it's okay?
Yes, it's okay.
Yeah.
Yeah, let me just define these parameters, which are very classical in multi-field cosmology. So they are called kinematic parameters. So what they are functions of t, real valued functions of t, which are associated to a given cosmological curve. So you define the first, second, and third Hubble slow roll parameters. This comes from a deeper theory, the theory of slow roll expansions, but I won't go into that. So they are denoted traditionally by epsilon, which is minus h dot over h. So remember that h was the logarithmic derivative of this a of t, which was, of course, ultimately determined by a cosmological curve. So here we can do some substitutions and reduce this to a reduced observable, to a function defined on some open subset of the tangent bundle to your surface M. Eta parallel, which is the second Hubble slow roll parameter, is defined by this formula. It's minus sigma double dot over h sigma dot. And psi, which is the third Hubble slow roll parameter, is given by this sigma triple dot over h square times sigma dot. Of course, everything is evaluated at a cosmological time t, which is inside the interval I of definition of your cosmological curve. So these are cosmological observables. These are examples of what I called cosmological observables, which are of higher order. And what will happen later is that you can reduce them modulo the cosmological equation through that on-shell reduction process to obtain functions which are defined on some open subsets of Tm. So this is an example that illustrates that general abstract idea that I tried to sketch before. But you also have other parameters. You have the so-called first and second term parameters. These are denoted usually by eta perp and nu. The eta perp is just omega divided by h. So remember that omega was this, again, it's a cosmological observable given by that formula. And nu is the time derivative of eta perp divided by h times eta perp. So again, it's nu is a higher order cosmological observable, which can be reduced to a first order cosmological observable modulo the cosmological equation. And finally, you have the first infrared parameter, kappa. That's a terminology that comes from one of my older papers. It's not classical terminology in cosmology. And the conservative parameter, which was introduced for the first time in my paper with Lilia. They turn out to be useful for certain expansions, which I won't go into, but they will appear later. So this is kappa is just sigma dot square over 2v. It naturally comes from this Hubble function. And C is by definition just h sigma dot divided by the norm of the differential of v. So again, the norm of the differential of v is with respect to the metric induced by G on the cotangent bundle of M, right? Because the differential of v is a section of the cotangent bundle of my surface calligraphic M. All norms are with respect to the natural metrics induced by G on the corresponding natural bundles. Good. So there's a certain quantity. There's a remark which is not going to be important, so I skip over that. So finally, let me mention the slow roll and repertoire conditions. These are the conditions that physicists use, which will appear in the definition of what they want to call, what we call SRRT inflation, which is really the kind of inflation they want to have. So this is where the physics come in. So you can, for the rest of the talk, I will simplify things by taking the Planck constant to be 1, which means I'm measuring everything in Planck units, which correspond to saying that a rescaled Planck mass is equal to square root of 2 over 3. One way to justify why you can fix the value of the Planck mass is to notice that there exists a certain similarity of the cosmological equation, which comes from various scalings, which can be used to fix the value of the rescaled Planck mass to any positive real number you want. So that's, of course, again discussed in in one of the papers of mine that I mentioned before. So there's
The
a
first and the third point, is there a typo? Maybe shouldn't be look
Where?
like the same. The first and the third point look like the same. Maybe there's the second line.
no, it's not. Wait a moment. So let me finish what I have to say, and I will explain in a moment. So there's in fact a two-parameter group of similarities of the cosmological equation, which is discussed in my paper, and you are using one such similarity to fix it. So I will take m naught to the square root of 2 over 3, which amounts to working in Planck units where the Planck mass is equal to 1. So by definition, the first, second, and third slow roll conditions are the conditions epsilon much smaller than 1. Epsilon was the first slow roll parameter, adiabatic slow roll parameter. Absolute value of eta parallel much smaller than 1, respectively absolute value of psi much smaller than 1. So I don't have an absolute value in the first slow roll condition because epsilon, the first slow roll parameter, turns out to be always positive. Okay, it's just a fact of life. The second order, and that's part of the answer to your question, the second order slow roll regime is a combination, is defined by a combination of the first order slow roll condition and the second slow roll condition. And the third order slow roll regime is defined by a combination of the first order slow roll condition, second order slow roll condition, and third order slow roll condition. So you have three logically independent conditions: the first order, the first slow roll condition, the second slow roll condition, and the third slow roll condition. And you can combine them, right? You can combine them in three ways, because there are three ways of choosing two conditions out of three. Or you can also join them together. You can impose all of them simultaneously. So it is important for us to consider the following combination of these conditions. When you impose the first and second of them simultaneously, that defines the second order slow roll regime. And when you impose all of these three conditions simultaneously, this defines the third order slow roll regime. Does this answer your question, Thomas?
And the slow roll regime is just epsilon much smaller than 1, I guess, no?
That's the first slow roll regime. I mean, there's a lot of confusion in the way physicists use this stuff. So in most of the cosmology literature, they are extremely careless about language. Strictly speaking, you can consider an infinite order slow roll regime. So there exists a generalization of this, and I discussed them in another paper of mine, to arbitrary order. Okay. And there's a so-called slow roll expansion, which is a formal expansion, which in good situation is asymptotic and so on. So there's a generalization of this. You can actually define higher order slow roll parameters. So I considered only the first three of them. You can define four slow roll, 5 slow roll parameters, 6 slow roll, and so on up to infinity.
Okay.
And strictly speaking, slow roll or perfect slow roll means that you require all of them to be much smaller than 1. But if you require only the first case of such parameter to be much smaller than 1, that's called the case order slow roll regime. And if you require only some of them to be much smaller than 1, you have to specify which of them. So the simplest condition that you require is first order slow roll, and first order slow roll is equivalent to first slow roll. So case slow roll means that you require the case order parameter, the case slow roll parameter to be much smaller than 1 on its own. Case order slow roll means that you require the first k parameter, including the case, to be all smaller than 1 simultaneously. That's the general framework. Is it clear?
Yes.
Okay, good. So now you also, by definition, consider the rapid turn condition, which is a condition that the absolute value of eta perp, it's one of the parameters I defined before, it's omega over h, whatever, is much bigger than 1. So of course, that's equivalent to saying that 1 over eta perp is much smaller than 1. Okay? And you also consider the sustained rapid term regime, which is defined by joint conditions, by two conditions, namely the rapid term condition together with a further condition, which is the absolute value of nu much smaller than 1. So nu was another parameter I introduced before, this, the second term parameter. So if you require 1 over the first term parameter to be much smaller than 1, and the second term parameter much smaller than 1, that's called the sustained rapid turn regime. And that's the kind of regime that we are going to be interested in. And to explain why this conservative parameter is relevant, there's a following proposition, which is simply easy to show after you do this dynamical reduction to reduced observables, first order observables. So you can show that if the second slow roll condition, absolute value of eta parallel much smaller than 1, is satisfied, then the rapid turn condition, which was 1 over eta perp in absolute value much smaller than 1, or equivalent eta perp in absolute value much bigger than 1, is in fact equivalent with what we call the conservative condition, which is a condition that C is much smaller than 1. That equivalence holds on shell, so modulo the cosmological equation. So after reduction of all these slow roll and rapid turn and whatnot observables, which are in general higher order observables, to first order observables modulo the equation motion. So that's, and I will stop here and give you a break. Okay?
Okay.
Okay, so I propose that we take like 10 minutes break, which means that we meet again in 3:30 Warsaw time. And Calin, please remember that you have half an hour after that.
Okay, good. So 10 minutes, yes?
Yes, Emma. Okay, it's 3:30 Warsaw time, so I suppose we should start the
Okay.
second part.
Okay, so I start now, yes?
Yes, yes, you start now and your slides are not visible. They appear. Great.
Okay, so the next thing I have to explain, and after this we can enter into the meat of what we did, is the so-called adapted frame. Okay, so I'm going to consider the complement of the critical locus of the scalar potential. So remember, V was a positive, strictly positive, real valued function defined on my surface M. So it has a critical locus. It's a locus consisting of those points in my surface where the differential of V vanishes. And I consider its complement. The critical locus is obviously a closed subset of M, so its complement is an open subset of M, therefore it carries the open submanifold structure. So I denote this complement of the critical locus by M0. It's an open submanifold of my surface. Okay? So the adapted frame of my scalar triple MGV is an oriented orthonormal frame of this non-critical locus, of this open submanifold M0, which is defined by the vector fields n and tau given in this formula. So n is just a normalized gradient vector field of V, and tau is the vector field obtained by rotation by plus angle plus pi over 2 from n. So it's again a normalized vector field defined on this non-critical locus M0. So the reason why I have to restrict to a non-critical locus is precisely to be able to define this normalized gradient vector field, because the gradient vector V obviously vanishes on the critical locus. So in order to avoid dividing by 0, having an expression of which is essentially 0 over 0, I have to restrict to the non-critical locus of M. So this is a positively oriented orthonormal frame of the non-critical locus of this open submanifold M0, which is in general non-holonomic. So it doesn't come from a coordinate, local coordinate system on M0. It's a non-holonomic oriented orthonormal frame of M0. It's called the adapted frame of my scalar triple. There's something called the characteristic angle. I will jump over this since I have a bit of a time because it's not going to be very important. Okay, so now finally I can explain what I meant by consistency conditions for SRRT inflation. So SRRT is an abbreviation for what we call sustained rapid term with third order slow roll. Okay, so in order to state them, I have to state first a preparatory proposition. For this, I introduce the following notation. If I give you two vector fields xy on this surface calligraphic M, I'm going to use the notation Vxy for the Hessian of the scalar potential V applied to the pair of vectors x and y. So remember, the Hessian is the Riemannian Hessian. So V is a real valued function defined on M. I have a Riemannian metric on M, so I can consider the Riemannian Hessian tensor of V with respect to G. I denote this by Hess V without indicating the metric G. It's a symmetric covariant to tensor defined on M, so a section of the second symmetric power of the cotangent bundle of M, so I can evaluate it on a pair of vector fields xy, and I denote the result of that evaluation by Vxy. So Vxy is a real valued function defined on M. Okay? So the Riemannian Hessian, I remind you, is defined invariantly as nabla of dV. dV is the differential of V, so it's a section of the cotangent bundle. And nabla is a connection induced by the Levi-Civita connection of G on the cotangent bundle of M. So it's simply nabla applied to dV. And it's easy to prove that it's symmetric. That follows from the fact that G is a Riemannian metric, so it's torsion-free. Okay. Then the proposition states with this notation that you have the following two relations. So VTT defined by 3h squared is equal to omega squared over 3h squared plus epsilon plus eta parallel minus psi over 3. And VTN divided by h squared is omega over h. multiplying what's in the parentheses. So the parenthesis contains 3 minus epsilon minus 2 eta parallel plus nu. So these are the kinematic parameters, some of the kinematic parameters that I introduced before. So in the first relation, you have the first, second, and third adiabatic slow roll parameters, and then you have this thing, omega was sometimes called the turning rate. And in the second, you have the turning rate divided by the Hubble parameter, multiplying some expression which contains the first and second slow roll parameter, adiabatic slow roll parameters, and the second turn parameter nu. This follows by a computation, and I studied it as a proposition. So now with this, you can prove the following theorem. Here I'm using something called the characteristic angle, so I have to define this. So the characteristic angle of a cosmological curve, so cosmological curve was a solution of the cosmological equation at a point t inside the interval definition of the cosmological curve, is the angle of rotation from the adapted frame n tau considered at the point phi of t. So I'm assuming that this is a so-called non-critical cosmological curve, namely a cosmological curve whose image is contained in a non-critical locus m naught. So it's the angle of rotation from the frame n tau evaluated at phi of t to the Frenet frame Tn at the point phi of t. Okay, so it's given by these formulas where, of course, everything depends on t implicitly, but I don't indicate the dependence on t. So big T is n cos theta plus tau sin theta, and big N is minus little n sin theta plus tau cos theta. And I take its determination to be in the interval minus pi pi, which is semi-closed. So it's open at minus pi and closed at pi. It's an interval length to pi. I choose the determination for convenience. And there's also a related quantity, the so-called characteristic sign of phi, again at a point t in its interval definition, which is the sign of the characteristic angle. The characteristic angle can have 0 sinus. The sign of the sinus of the characteristic angle, which turns out to be, because of my choice of determination, the same as the sine of theta. It can be valued, it's valued in minus 1, 0, or 1. So it's equal, S is equal to minus 1, 0, or 1. And there are certain relations which are given that proposition, but I will jump over them. Okay, so we can prove the following theorem with these preparations and notations. Suppose that the third order slow roll conditions are satisfied. The third order slow roll condition is satisfied. So this means that epsilon is much smaller than 1, absolute value of eta parallel much smaller than 1, and absolute value of xi is much smaller than 1. All these three conditions are satisfied simultaneously. And moreover, that the small rate of term condition, absolute value of nu much smaller than 1, is also satisfied. So notice that you have three conditions which require that 3 parameters are much smaller than 1, 4 conditions which require that 4 parameters are much smaller than 1. So this is the kind of framework that I mentioned before. Absolutely. In this case,
these equations which follow, are they functions of time, or how do you view it?
Everything is at, yes, everything is, there are functions of the point phi of t.
Yes, and there are no constraints on G and V yet, right? Which you announced that there will be some constraints.
Not yet, there will be at the end of the theorem. So let me finish stating the theorem and I will explain.
Sure.
So in this case, certain approximations hold for the characteristic angle, and furthermore, certain other approximations hold for this VTN, VTT, and VTAN. Of course, these are evaluated at the point phi of t, right, for a cosmological curve, because these parameters depended on a point in the tangent bundle of M that has a projection, which is phi of t. So they are evaluated at that projected point. Okay? And these equations admit a solution C. So you see, you can view this as a system of equations. So the last two equations form a system of equations which you can view them as equations for, which you can view as equations for C. And you can solve for C, and the statement that these equations admit a solution C, which happens to be much smaller than 1. So C, this conservative parameter is always positive. So they admit a solution C, which happens to be much smaller than 1, if and only if this relation is satisfied by the scalar potential. So V and tau squared. This was the Hessian of V on this adapted frame n tau, so evaluated at the vectors n and tau. V and tau square times V tau tau, this is a Hessian of V as evaluated at tau and tau, is approximately equal to 3V times V and n squared. This is a Hessian of V as evaluated at n, n. Where, of course, approximate means that there is an expansion in certain small parameters, and I don't write the order of the correction. There's a plus of something, of course. There's an equal to this plus of something, but I write it in this schematic form to simplify the presentation. Okay. Thomas, so do you have further questions?
So I imagine that this last equation comes from the first equation of the three, right?
Yes, modulo this condition that there is a solution with C much more than one.
So you plug in the second and the third into it, and then what?
Yes, so I mean, you combine this, so you assume that C is, that there is a solution of the second and the third with C much more than one. And then you do some algebraic manipulations using the first equation. You plug something in the first equation. It's a bit more complicated than that, but
okay.
You have to read my paper with Lilia. It takes about a page and a half to do this because you have to be careful with certain approximations and the orders and so on, but we do it carefully.
Okay.
Okay? So I just stated the final result. So this is the approximate version of what I will call the SRRT equation. So I will call the imposing all these conditions simultaneously, including C much smaller than 1, the SRRT condition. Sustained slow roll with rapid turn. These are the conditions that are relevant for something called SRRT inflation in physics, but here I focus on the mathematics formalism. And the claim is, and it's related to what I said before as a general argument coming from the implicit function theorem, because that's what's going on conceptually behind all these computations, that unless this condition is satisfied up to some higher order correction, you can never find such curves. So such curves which satisfy this SRRT condition can only be found in a region of the surface M, target surface calligraphic M of the model, where this equation is satisfied up to some higher order correction. So if you impose this equation on the nose, so with strict equality, ignoring the higher order correction, the corrections are in all the parameters, epsilon, eta, psi, nu, and c. It's a complicated higher order correction. Then that's called the SRT equation. Okay. Yes? Okay. So let me extract the part that has immediate mathematical interest from this. So the corollary is that the cosmological curve phi, so solution of the cosmological equation, satisfying the sustained rapid turn conditions with third order slow roll at cosmological time t, if and only if the following condition is satisfied at the point m equal to phi of t of m naught. So I assumed throughout that this phi is a non-critical curve. The image of phi is contained in a non-critical locus. Doesn't mean the critical locus of V. Okay? So that's the equation. So the SRT, the strict SRT equation, and that's where we are headed, by definition, is the following condition. So you impose, instead of using an approximate sign here, you use a strict equality. You neglect the higher order correction. Is the following condition which constrains the target space metric G and scalar potential V of the non-critical submanifold M naught of my model. So V n tau squared times V tau tau is equal to 3V times V n squared. If you fix the scalar potential V, then you say that the metric G on M naught, which satisfies this equation, is an SRRT metric relative to V. Now, I will jump over this. It's done in detail in my paper using the standard formula of geometric ODEs, which uses the formulas of jet bundles. So it can be shown that the SRT equation can be written as a nonlinear geometric differential equation for the pair GV on this open submanifold M naught, in the sense that there exists a certain function defined on the relative Whitney product of the first jet bundle of curves of M naught with the second jet bundle of curves of M naught, which you require to be equal to 0. So it's in a standard sense of geometric nonlinear PDEs. It's a nonlinear PDE, which is of first order in G and second order in V, where GV are sections of certain bundles defined by M naught and so on. Okay. When G is fixed, this can be viewed as a nonlinear second order PDE for V, and when V is fixed, it can be viewed as a nonlinear first order PDE for G. So you can find the gory details of this formulation, which is of course somewhat not surprising in my paper preprint, with Mirela and Victor. So what we are going to do next, in order to simplify this, right, if you want to choose coordinates, and we are going to fix a scalar potential and want to look at it as an equation, first order equation for the coefficients of matrix G. But G has 3 independent coefficients because this is a surface, M naught itself is 2-dimensional. And it's complicated because, of course, you have to consider the gauge freedom given by changing longer coordinates, and we don't want to deal with that. So the trick we are going to use is to fix the conformal class of G, which, as I mentioned before, is equivalent to fixing the corresponding positive complex structure on this M. The moment I fix the conformal class, I fix the corresponding positive complex structure. So my scalar manifold M, my target manifold M, becomes a Riemann surface. M together with J, with a fixed complex structure, is a Riemann surface. But as I mentioned before, in almost all physics applications of interest, this is a non-compact Riemann surface, a borderless non-compact Riemann surface. Therefore, its topology can be very crazy. It is well known that oriented, well, even unoriented, but oriented non-compact surfaces have a very complicated topological classification because, which is not just given by the genus, as in the compact case, because you have to consider the genus together with the topological space obtained by the so-called Karakerto-Stoilov compactification, which is a particular case of the theory of ends of Freudenthal. It's a particular case of the Freudenthal compactification. It was studied 100 years ago by a Hungarian mathematician, Karakerto, and a Romanian mathematician, Stoilov. The Simeon Stoilov Institute of the Romanian Academy was named after him because he was, I think, his first director. Okay, so you have to consider this Karakerto-Stoilov compactification, which is a particular case of the Freudenthal compactification, and the space of ends can be very crazy. In particular, it can contain a Cantor set and so on and so forth. So I warn you that the theory of non-compact Riemann surfaces is much, much harder than the theory of compact Riemann surfaces. So in general, this will be a non-compact Riemann surface as soon as you fix the conformal class of G. And that's what we are going to do. So I'm going to consider the fiber bundle of positive definite symmetric tensors on M. So this is an open subbundle of the bundle of symmetric covariant two tensors on M. I call it S plus. When the scalar potential is fixed, the SRRT equation can be written as a geometric first order PDE for sections of S plus, right? Because G is a section of this S plus. It's a strictly positive symmetric two tensor, covariant two tensor. So this takes a standard form of the geometric first order PDE for sections of S plus, which is F of J1 of G equals 0, where J1 of G is the first jet of this section. And F is a smooth function which depends on V, which I'm going to compute. Okay. So to give a nicer formulation of this, so to give a nice formulation of fixing the conformal class of G, I'm going to consider the determinant, real determinant line bundle of M, which by definition is the second exterior power of the cotangent bundle of M. And L plus to be the open subbundle of positive vectors. What I mean by this is that, of course, M is oriented. So inside every determinant line, there is a distinguished half line, which agrees determined by that orientation. That's a positive half line. And I'm considering the bundle of such positive half line, which is a fiber bundle whose fibers are diffeomorphic with a positive half line. Okay, that's L plus. So fixing the complex structure J determined by G, you can show that the map which takes G into its volume form, omega, gives an isomorphism of fiber bundles from S plus into L plus, which induces, of course, an isomorphism between the first order jet bundles, J1 of S plus and J1 of L plus. Using this isomorphism, you can transport this function F to a function Roman F, which depends on J and depends on V. J was the complex structure determinant conformal structure of the metric, which is a function defined on the first order jet bundle of L plus with values in R. And the SRRT equation becomes this Roman F of J1 of omega is equal to 0. So here, I think Janusz should be extremely happy because this is a standard form of a contact Hamilton-Jacobi equation.
Calin,
Yes.
I'm a bit lost about this isomorphism. So S plus is essentially a rank 3 vector bundle in S.
Yes. Yes.
L is a line bundle. So how do you get an isomorphism?
Because I fix the conformal class of a metric. So you see, there was this algebraic equation which related G of UJV to omega of UV. J is, of course, determined by G, by the metric. But if you fix J, then you lose all of the information in G except omega, except its volume form.
Probably the conformal class.
Let me give you the intuitive idea because it's actually very simple. So if I fix the conformal class of a metric, all that I'm left with is a Weyl rescaling, right? It's a Weyl scale of the metric. I can rescale the metric by a positive function.
Yeah.
That's all the information. But rescaling the metric by a positive function is the same thing as rescaling the volume form of the metric by the same positive function. Because
I just want to say that the conformal class properly fixes a half line inside S plus.
No.
But then how can it be? I mean, this is different dimensions, right? They have different dimensions, the fibers. So
yes, of course, they have different dimensions. Right? Well, the conformal class here fixes a half line inside L plus, which is diffeomorphic with inside S plus, which is diffeomorphic.
That's what I'm saying.
Okay. Then yes, you are correct. Yes, that's exactly what it does. And your point is very important because that's exactly the simplification that happens. If you fix a conformal class, you are left with a single degree of freedom, which is this Weyl parameter. This conformal exponent is sometimes called of the metric. So you lost all of the information about the shape of the metric and you just remember its local scale. So of course, it's a huge reduction, huge simplification. That's exactly why we are doing it. We reduce the rank from 3 to 1, which is what I wanted to do. So there are two ways to simplify. One is to deal with this. One is to work in local coordinates with the coefficients of the metric. There are 3 coefficients. But then you have to deal with the problem of changing coordinates, right? The gauge freedom. And that's quite complicated. Fixing the conformal class is much smarter. It's some kind of partial gauge fixing, but it's a very smart partial gauge fixing. You fix the conformal class of a metric, and then you are left with a single degree of freedom. Okay? And we found this, I found this to be much easier than to deal with this issue of gauge freedom from changing coordinates. So that's why we're doing this, because and also it's very nice because you actually relate to the theory of non-compact Riemann surfaces, generally non-compact Riemann surfaces, and you have a lot of tools at your disposal. But yes, that's a key conceptual point. So here I'm giving you without formulas. In a moment, you'll see very complicated formulas. And this contact Hamilton-Jacobian, contact Hamiltonian F is very complicated. So the point is that once you fix this conformal class of the metric, the SRRT equation becomes a contact Hamilton-Jacobi equation for the volume form of the metric. The volume form of the metric you can view abstractly just as a section of this bundle of positive half lines, L plus. And of course, this contact Hamiltonian is defined on J1 of L plus, which carries, as everybody knows, the Cartan contact structure. It's a natural contact structure on the first order jet bundle. On the first order jet bundle. So this is a very, very natural equation. Yes? And
but here phi is a function on M which is real, yes?
Phi or F? Which?
The problem of notation, you used phi for a different object. So here phi is different.
What phi? I'm not using phi, any phi here. I'm using F.
Scalar field. Scalar field was phi. And
yes.
Here phi is conformal factor.
Yeah. There are two phis. There is a round phi and there is a below. You already jump below. Yes, I mean this should be. Yeah, I made a typo here. So we have two phis in our preprint. One is round phi, which was the scalar field, and the other one is the Roman phi. And I should have used the Roman phi. Okay, the Roman phi is a scalar exponent of the metric. So yes, you are right here. I made a typo, and I will correct it before I send you the final version of transparencies. Before I send Cassia the final version of transparency. Yes, this should be a Roman phi. You are correct. So how do I understand what this equation tells me? Of course, I can choose local isothermal coordinates for M relative to my given complex structure, right? So I'm also choosing a local complex coordinate for the complex Riemann surface given by the pair MJ, right? I endowed them with a complex structure, so it's a complex Riemann surface. I can choose a local complex coordinate Z, and I take the real part of Z and the imaginary part of Z. I call them X1 and X2. These are the standard, the classical local isothermal coordinates of M relative to the given complex structure J. And they are defined on some open submanifold of M. There is always an open neighborhood of every point of M which admits such coordinates. It's a very classical result from the 19th century. So in such local isothermal coordinates, the metric is conformally flat. It can be written as E to 2 Roman phi again. Thank you, Janusz, for pointing this out, times the Euclidean metric with respect to coordinates x1, the isothermal coordinates x1 and x2. And the volume form is E to the 2 phi times dx1 with dx2. So you can see very explicitly that the only degree of freedom left in the metric is the scalar exponent Roman phi. So again, I think I made this. I was careless with this notation throughout. So from here on, this little phi should be the Roman little phi. Okay, sorry for that. I was careless last night. I didn't notice this typo. Okay. So using these formulas, you can write this Hamilton-Jacobi equation very explicitly, and I will do this in a moment, as a nonlinear first-order PDE for this conformal exponent. Some people call it conformal factor, though I think correctly e to the 2 phi is conformal factor. Let's call it the conformal factor, phi, which is cubic, turns out to be cubic in the partial derivatives of this conformal exponent phi. And the change of local isothermal coordinates turn out to correspond to a contact transformation. Okay, so now I finally can get into the meat of the talk, and I don't have much time left. So the content, what is the form of the contact Hamiltonian in isothermal Liouville coordinates? So what are isothermal Liouville coordinates? If I choose these isothermal coordinates on M naught, in fact, relative to J, then I can lift them to some kind of natural Liouville coordinates on J1 of L plus, which I call isothermal Liouville coordinates. And they are defined precisely in our preprint, but I don't want to discuss this here because I don't have time. So let G naught be the locally defined flat metric with square line element dx1 square plus dx2 square relative to some choice of isothermal coordinates x1 and x2. and define the modified Euclidean gradient of V through this formula. So it's basically the Euclidean gradient of V, so the gradient of V with respect to this local Euclidean metric, to which you apply the complex structure J, complex structure operator J. So grad naught of V is grad V with respect to this Euclidean metric, okay? And then you are going to use more notation, so you define H naught and H tilde naught to be the Euclidean Hessian of V applied on grad naught V and grad naught V, respectively grad naught V and this modified Euclidean gradient, J grad naught V. I gave you here the local expression in isothermal coordinate. Epsilon is the var epsilon is the ordinary epsilon tensor. Okay. So I'm going to choose an open subset of this non-critical submanifold M0 and let you not be image through the isothermal coordinates x1 and x2, which is a subset of R2, an open subset of R2. And I mentioned this isothermal Liouville coordinates. I denote them by x1, x2, u, p1, p2. I won't go through that definition. So x1, x2 are coordinates. U is the famous contact coordinate in contact geometry, and P1 and P2 are the momenta. So you can, that's a physical interpretation. They are defined locally. So these isothermal Liouville coordinates, whose definition I didn't give, induce an isomorphism of Weisberg bundles between J1 of L plus restricted to U and this open subset U naught cross R2. So you can see what's the local structure of your contact manifold. Then you have to consider two smooth functions defined on U naught cross R2 valued in R given by these formulas. And you notice that they give a linear transformation which is non-degenerate for any point in U naught and has this inverse. And finally, you can prove the following theorem that in isothermal Liouville coordinates on Gen 1 of L plus restricted to U, the contact Hamiltonian is given by the smooth function f defined on U naught cross R3 valued in R given by the following expression, where I defined A and B before. So it's that complicated. It's a very complicated expression. And the contact Hamilton-Jacobi equation takes the standard contact Hamilton-Jacobi form. There's some question? Is there a question, Kasia?
No, sorry. This was just an unrelated comment.
No, if there's a question, please ask it so I can clarify. So here is basically a bunch of notations to write this equation, because if I write it without the notation, it's even more complicated. So the important thing is that it's cubic in momenta, and it depends in a complicated way on the coordinates, and it depends on the exponential of this contact coordinate u. Okay, so it becomes, of course, locally a standard contact Hamilton-Jacobi equation. Now, of course, this is a general fact, of course, in the theory of PDEs. You can try to solve the contact Hamilton-Jacobi equation through the method of characteristics. That method only works locally, and you need some kind of regularity conditions. And of course, we go through that, and we compute some characteristics numerically, and so on and so forth in our preprint. But much more interesting and important is the observation that the contact Hamiltonian is proper in the sense of Crandall and Lyons, which means that it is non-decreasing in the contact coordinate u. Therefore, the Dirichlet problem, and not only that, also the mixed and von Neumann problem, for this equation can be approached globally using the theory of viscosity solutions. So hopefully, at least some of you heard of the work of Crandall and Lyons on viscosity solutions, which is now a very well-developed subject in the theory of PDEs. Okay. So you can expand this. I can give you some more details of how this contact Hamiltonian looks like. It's given by some formulas. One important thing to look at is how this Hamiltonian depends on momenta, right? So for this, I'm going to study the so-called momentum curve of this equation. So the momentum curve is a curve at a point xu. So I fix the coordinates x1 and x2, my isothermal coordinates, and the contact coordinate u. And if I do that, I can look at the equation f of x1, x2, u, p1, p2 equal to 0. Since x1, x2, and u are fixed, that's an equation for p1 and p2. P1 and p2 are inside some plane, R2. And as I said, f is cubic in p1 and p2, so that defines a cubic affine curve, a cubic real affine curve. That's the momentum curve cxu. And to study it, it's convenient to shift the momenta by some quantities in order to bring it to a simpler form. So first of all, you notice that this momentum curve passes through a certain distinguished point of the p-plane, which depends on x and u. It's given, the formulas are given here. It depends actually only on the x1 and x2, not on u. And it's important to study whether this curve is connected, irreducible, where it has its singular points and so on, because this gives you information about the qualitative behavior of this convex Hamilton-Jacobi equation and where you could have shock waves developing and other things. I don't have time to give too much detail. So you notice that the singular points of the momentum curve coincide with the characteristic points of the convex Hamilton-Jacobi equation. So,
Calin, I'm sorry to interrupt, but it is now like 6 minutes after the time, and some of us have lectures. So could you please somehow wrap it up?
Yeah, so I can wrap it up. So you can study this momentum curve. I'm just going to give you some drawings. There are 3 cases of how it looks like. And you can then apply the theory of viscosity solutions. So one of the things it gives you is that you consider, you can approximate solutions of the Cauchy problem for this equation by doing a so-called viscosity perturbation, which means that you add to the equation a term which is proportional to the Laplacian, the Euclidean Laplacian of V, multiplied by a positive constant, which is called the viscosity parameter. And you can vary the viscosity parameter. When you take the viscosity parameter to 0, you are supposed to approximate a viscosity solution. A viscosity solution is a generalized solution, which is differentiable only outside of measure 0 subset, so you can develop shocks, okay? And you can prove many more things. This is only a fraction of what we have in our preprint, but I'm going to jump over it. You can consider various approximation. I'm going to jump at the very end and show you some graphs of viscosity approximants of these solutions. So here you can see some projected characteristic curves. This is a certain choice of the potential. I choose a certain Cauchy problem with boundary conditions, Cauchy boundary condition on a circle. And here is a viscosity approximant for a small value of the viscosity perturbation, which is e to minus 7 of the viscosity coefficients. And here I'm going to show you some other graphs. Again, some projected characteristic curves. This is another potential, V, that I'm considering, and another viscosity approximant for this situation. I'm done. Cassiel, you should have let me know in advance that I'm running out of time. But anyway, so I'm done. I simplify. So the point is, the upshot is that you can use these viscosity perturbations to give viscosity approximants, and you can, of course, do many other things. There are natural approximations, a quasi-linearization, and even a linearization of this equation around isolated critical points of the non-degenerate critical points of the potential, and many other things. And you can find this in our preprint. So there's a lot more that you can say about this equation. The upshot is that this equation is not impossible to study, and you can study some regimes of approximation quite precisely, and you can also approach it very explicitly numerically using the theory of viscosity solutions and viscosity perturbations. So it is actually a manageable equation. You can do many things with it. The result is that you can build models which are called fiducial models, models for which this SRRT consistency condition is satisfied on the nose throughout this non-critical submanifold. So these are, in a certain sense, ideal approximation, the idealized model, the best possible models in which you can realize SRRT inflation. And that's a conceptually important result because the existence of such fiducial models was not known. It's very hard to build models in which you can realize SRRT inflation. And somehow the upshot is that good models should cluster around these idealized models, around these fiducial models. So that rules out the vast majority of models that you can write down. It gives you, for example, if you want to realize SRRT inflation in string theory, it's going to be extremely constrained. There are going to be very few string compactifications in which you can realize this kind of inflation, which I think is a conceptually important result. I'm done.
Thank you very much. I propose that we thank the speaker. And I must say that I'm very sorry that I personally cannot participate in the discussion. And since everything is on my computer, I have to switch it off in a moment and go to the next, assignment that I have. However, if you want to discuss, I can pass a host rights to somebody, and you can just stay on. So please, if you want to discuss things, so maybe I will just do this. I will make Calin the host, and then you decide, yeah, and I will disconnect. So thank you very much.
Okay. Sorry for being out of time. I apologize for it. I didn't know because you didn't tell me.